industrial anomaly detection is evolving. We've moved from single-class models to multi-class and cross-class systems, but the ultimate goal is general anomaly detection, or GAD. The dream is a model that can detect anomalies in entirely new, unseen product categories, without needing any retraining or fine-tuning on target data. Multimodal Large Language Models, or MLLMs, seem like the perfect candidates for this. They have incredible visual understanding and reasoning capabilities. However, there's a massive gap. Most MLLMs are trained on web data, which looks nothing like a factory floor. Furthermore, existing anomaly detection datasets are primarily image-based, making them unsuitable for training the reasoning-heavy nature of an LLM. To bridge this gap, researchers have introduced MMR-AD, a large-scale, multimodal reasoning-based dataset designed specifically for industrial anomaly detection. The scale of MMR-AD is significant. It aggregates data from 14 public datasets, covering 188 product categories and 395 different anomaly types. We're talking about over 127,000 samples. But it's not just about the quantity, it's about the quality. The team manually reviewed nearly 190,000 images to strip out low-quality samples and added precise bounding box annotations for the anomalous regions. The real innovation here is the text. Instead of simple yes-no labels, MMR-AD uses a think-then-answer format. To achieve this, the researchers built an automatic pipeline using Qwen 2.5 VL72B. Here is how it works. The model is given a pair of images, a normal reference sample and the input sample. It's then prompted to perform a step-by-step comparison. By providing the model with visual hints, like red bounding boxes, and textual hints, such as the specific anomaly type and coordinates, the pipeline generates a detailed chain-of-thought reasoning process. For example, instead of just saying defect, the model explains that it's comparing the input to the reference, notices a missing cable in a specific position, and then concludes that the image is anomalous. This transforms the dataset from a simple classification tool into a reasoning benchmark. To test this, the researchers benchmarked the current state-of-the-art generalist MLLMs, including GPT-5, Gemini 2.5 Pro, and Qwen 2.5 VL. The results were a wake-up call. Even the most powerful commercial models struggle with industrial AD, particularly with precise localization. In many cases, these models suffer from hallucinations. They might correctly identify that an image is abnormal, but completely miss the location or invent a defect that isn't there. To address this, they developed a baseline model called Anomaly-R1, based on Qwen 2.5 VL7B. The training of Anomaly-R1 happens in two critical stages. First, there is a cold start initialization. Because general MLLMs aren't familiar with industrial defects, they use supervised fine-tuning on the MMR-AD dataset to teach the model the basic format and the nature of the task. Second, they apply reinforcement learning using an algorithm called GRPO, or Group Relative Policy Optimization. Unlike standard RL, GRPO doesn't require a separate value model. It computes the relative advantage of multiple responses to the same query. They implemented a specific reward function to keep the model honest. There is a result reward for the correct yes-no answer, but they also added a consistency penalty. This prevents the model from cheating, where it might guess yes correctly but fail to actually locate the anomaly. If the intersection over union, or IOU, of the predicted bounding box is less than 0.5, the model is penalized. To further stabilize training, they used contrastive sampling. This ensures every query group has both positive and negative examples, preventing the gradient from vanishing when all responses in a group are equally correct or incorrect. Finally, they injected domain-specific knowledge into the prompts, telling the model exactly what types of defects are common for a specific product category, like broken or deformation. The results are impressive. Anomaly-R1 7B significantly outperforms the base Qwen model, and even rivals much larger generalist models in both detection and localization. The team also ran ablation studies to see what actually drives this performance. They found that the chain-of-thought reasoning is non-negotiable. Without those explicit thinking steps, the model's ability to generalize drops significantly. They also found that the normal reference image is vital. Having a gold standard to compare against is how humans detect anomalies, and it turns out MLLMs need that same visual anchor to be effective. In summary, MMR-AD provides the community with a massive, high-quality resource to move toward truly general anomaly detection. By combining large-scale multimodal data with reinforcement learning and explicit reasoning, Anomaly-R1 proves that we can move beyond simple pattern matching and toward a model that actually understands what makes a product effective.